my output equation is here, negative x1, negative x2, and then u. So those are my A, B, C, and D matrices. Si minus A is how we find our eigenvalues, okay? Si minus A, and S, the diagonal, I gotta subtract my A's. Now I take the determinant of Si minus A. That's how I find my eigenvalues, right? So that's S times S plus a third minus negative a half times a third. Okay, so in order to figure out the roots of this, because we're going to set the determinant Si minus A to 0 to find my eigenvalues. That'll tell me where the poles are. So to find the roots of this thing, I went into MATLAB and typed in roots and gave it the coefficients. And those are the roots. And you can see, because the real part of those roots is on the left-hand side of the plane, we know that it's a stable system. And we knew that it was a stable system going in because it's made out of RLC components, right? Okay, so remember way back in chapter 3, we found that to find an inverse of something, we can do the determinant over the adjoint of a matrix. Okay, so we're going to find the adjoint of this thing hopefully soon. And if you remember, the adjoint was, if I want to find this guy here, I cover up the row and column and then find the determinant here. Okay, and we do that for all three, and then you put in some pluses and minuses, whether or not the rows and the columns add up to an even or an odd. So row 1, column 1, this one will be positive, and it's just, the determinant of something is just, the determinant of a singular value is just itself. So that is the cofactor of that guy. And if I do this one here, let's see, row 1, column 2, it's, those two are canceled, I'm just left with a third, but it's negative because I'm in row 1, column 2. That's not, it's not half, it's a third. Did I say a third? I meant a third. I said a third. Okay, I said a third. All right, we go down here, and we're left with negative 1/2. And since we're in column 1, row 2, it's going to be a flip-flop, so that's going to be a half. And then if we go to the last one, we cover up these two, we're just left with S. And that's the cofactor of Si minus A. And then the adjoint is just the transpose of that. Okay, so now that I found the adjoint, I can actually use this equation to find the transfer function. Okay, so if you remember, the determinant, or sorry, the inverse of a matrix can be evaluated by the adjoint of that matrix divided by the determinant of that matrix. We already found the determinant of that matrix. That is this. We use it to find our eigenvalues. So that's 1 over the determinant, and then we have C, adjoint of A, B, and D. I'll stop there, and then we will evaluate this, and then we'll just use quickie Laplace analysis to do the transfer function of it, and you'll see that those two will turn out to be the same thing. All right, so my apologies again for being late, and for canceling class last week, and for the tornado warning. I tell you what, one of these weekends I'll come in on a Saturday and we will make up all those hours Saturday morning. Cool? I won't really do that. I will if you want to. Yes, I want you to use MATLAB code for all the problems except for the last one. And then just publish your results, print them out, and you can use all the code I gave you and modify it, and then, yeah. Just make sure to publish it. Don't send me an M file, send me a publish. That gives me the results. I sent you a reply. No, that's okay. But yeah, there's a typo in there. I left out a word.